We've been working a lot with probabilities so far, and there are a lot of different rules or possibly techniques to remember, though this one can actually serve to be valuable in place of all of these techniques, where really we can use a diagram to illustrate probabilities and then extract those probabilities from that illustration as needed. So the idea here is that we only need to use joint probability. So remember, when we look at the probability of two events happening, then it's the probability of one times the probability of the other. We can construct kind of a chain using a tree diagram, kind of like with counting methods to follow all the outcomes, but along the way having probabilities, the probabilities available. So suppose, here's our example, suppose a server farm has 3 particular servers that contain identical data. This way, if any one or two of the servers fails, access remains possible to the data. So each server is either it's on with probability 84%, we'll just assume that means that it's functioning properly, or it's faulty with probability 16%. Now notice that those two add up to 100%. There's our sample space of events for any one server. And now we have these 5 questions. What's the probability all 3 servers are on? What's the probability that exactly one server is on? What is the probability that all servers are faulty? And there's just a lot of questions here that we could either compute individually or build a tree diagram and almost trivially be able to answer these questions. And by trivially I mean very simply be able to do that. So what I'm going to start off with is server 1. So we have 3 servers. I'll just label server 1. So I'm going to draw a tree diagram. There's my root of the tree. And for the branches, I'm going to label these S1, S sub 1, and S1 bar. Okay, so on will be indicated by an S, and faulty will be indicated by S bar, okay, with the subscript of which server we're talking about. So server 1 could be either on or faulty. So what I'm going to label on the branches is the probability of that event. This one's 0.16. Now, that's just for server 1. From here, from each of these individual outcomes, think about these as outcomes, server 2 could either be on or off, or on or faulty rather. Okay, so those are the 2 possible outcomes for server 2. Now, it's not important to start with server 1. The goal here is really just to see that this tree all the way up to the top, that is the outcome where server 1 and server 2 are both on. Okay, and that indicates that if I wanted to know this probability of server 1 and server 2 being both on, I could take 0.84 times 0.84, multiply the probabilities, and list the probability off to the right. Now I'm also going to consider server 3, so I'm going to keep going. Now if server 1 is off, server 2 could still be, oops, labeled out 0.16. Server 2 could still be on, or it could be off. And 84% chance that server 2 is on. Keep in mind that server 1's status does not in any way affect server 2's status. They are independent events. We have no reason to believe otherwise. And if server 1 and server 2 are both on, here comes server 3. Server 3 could be on or it could be off. And that's going to be 84% chance that it's off, 84% chance that it's on, 16% chance that server 3 is faulty. Now, if server 1 is on and server 2 is off, server 3 could be on or, I keep saying off, but I mean faulty. So if I say that again, just know what I mean faulty. And then if server 1 is off, server 2 is on, server 3 could be on or I don't really need these circles here, it just sometimes helps visually. And then same thing, if server 1 and server 2 are both faulty, server 3 could be on or it could be faulty. Now you can see that at this rung we have 1, 2, 3, 4, 5, 6, 7, 8 possibilities. And if you think about it as counting, well, there's 2 possibilities for server 1 multiplied or paired with 2 servers for possibility, 2 possibilities for server 2 gives us 4 outcomes multiplied by each of the two states of server 3, which gives us the 8 outcomes. And so we'll have 8 total probabilities. Here, namely, if I follow up the branch, I'll have 0.84 times 0.84 times 0.84, which is 0.84 cubed. And I'm just going to calculate all of these probabilities. Maybe some of them I don't need, but it's relatively easy to do this. So this is about 0.5, we'll just say 0.59, rounded to 2 decimal places. Here I'll have 0.84 times 0.84 times 0.16, which we could write as 0.84 squared times 0.16. 0.84 squared times 0.16 comes out to about 0.11, rounded to 2 decimal places. So there's an 11% chance that server 1 and server 2 are both on and that server 3 is faulty. You can see the probability is that all 3 are simultaneously operating. And then here we have 0.84 times 0.16 times 0.84, which again is just 0.84 squared. So there's 2 factors of 0.84. But if you don't like that, you can do 0.84 times 0.16 times 0.84. You're going to get the same answer. This just makes it a little bit faster. And we already know that that comes out to 0.11. Here, following this set of branches, 0.84 times 0.16 times 0.16, you can see how quick and simple it is to follow and calculate these probabilities, because you just have to follow the little paths to where you want to get to, or you can backtrack if that's easier. For this 4th row, 0.16 times 0.16 times 0.84. So 0.84 times 0.16 squared, which is about 0.02. And here we have 0.16 times 0.84 times 0.84, server 1 faulty, server 2, server 3 working fine. And that's again just 0.84 squared times 0.16, which we already know that comes out to 0.11. Server 1 faulty, server 2 good, server 3 faulty is once again 0.84 times 0.16 squared, which comes out to 0.02. Server 1, server 2 faulty, server 3 working, 0.16 times 0.16 times 0.84. You can notice that there's a lot of repetition here, and that we already know comes out to 0.02. And then the most improbable outcome is that they're all simultaneously faulty, which is 0.16 times 0.16 times 0.16, or 0.16 cubed. Now we actually have to round this a little bit further. It's 0.004 if we're going to try to be as accurate as possible. Now, because we didn't round, we should have rounded to the 3 decimal places, but this does come out to approximately 1 because we've accounted for all the different outcomes. Think about it this way. Let's say that let's say this is 100% of our, we have a bunch of people, and people all start at this trailhead right here. Let's say it's a hiking path from above, and all of them end up somewhere, right? So all of these incoming hikers will end up at one of these 8 rungs, and therefore that helps us explain why in the end we should have 100% of all people accounted for, in this case 100% of all server outcomes. All right, let's see how easy this is to actually work with now. What is the probability all 3 servers are on? Well, that's easy. Server 1, server 2, server 3, it's 0.59. What is the probability that exactly 1 server is on? Okay, well that means just server 1 is on, just server 2 is on, or just server 3 is on. So let's see where just server 1 is on. Well, that would be S1 on, S2 and S3 both faulty. That's 0.02. So that goes into the calculation. Then it's server 1 faulty, server 2 working, server 3 faulty. That's 0.02. Server 1 faulty, server 2 faulty, server 3 working. That's also a situation where you have exactly 1. Notice the word exactly. Exactly 1 server is on. 0.02 plus 0.02 plus 0.02. Remember, there's no overlap here. These are mutually exclusive outcomes. 0.06, 6% chance that exactly 1 server is on. So in other words, there's a 94% chance that at least 1 server is I'm sorry, never mind, we'll come back to that. What is the probability that all servers are faulty? Well, that's easy. That's server 1 faulty, server 2 faulty, server 3 faulty. That's 0.004. And see how fast this is to answer. What is the probability that at least one server is on? Well, there's two ways we could do this. First of all, notice that the only outcome where none of the servers are working is this one. This is none of the servers working. Okay, so that means we would add up all of these guys here. Well, instead of doing that, instead of having to add a bunch of things, since we know that all of these 8 things sum to 1, we can just take 1 minus the probability of none. This is our at least one rule. At least one would mean 1 minus the probability that none of them are on, 0.004, which comes out to 0.996. There's a 99.6% chance that at least one server is working. Lastly, what's the probability that the first or second server is on? Okay, first or second server. Let's remember what the word or means. It means server 1 on, and server 2 off. Okay, that's just where just one of them is true. Server 1 on and server 1 off and server 2 on. That's the definition of the word or. It means the one, the other, both. So, or could also mean that they're both on. In other words, that at least server 1 or server 2 is on. Just be careful when you answer this question because it says nothing about server 3. So this is regardless of server 3 status. Okay, this just says only about server 1 or server 2. It doesn't say what must or must not be true about server 3. So let's just find all of the situations S1 and S2 not. Well, here's S1. S2 not is this bubble. S3 could be either on or off. So there's two outcomes where server 1 and server 2 bar, and that's 0.11 plus 0.02. That's the situation where server 1 is on and server 2 is off. There are two possible outcomes for server 3, neither of which is specific in this problem. Then there's server 1 is off, server 2 is on. Again, no indication of what's happening with server 3, so that's another 0.11 plus 0.02. And then finally, server 1 and server 2 are both on. Doesn't matter the status of server 3, that's going to be the 0.59 plus 0.02. I'm sorry, 0.11. So we have 0.13, and here we have a 0.7. Okay, notice again there's no overlap among these because they're all individual distinct branches that we've considered. You could go along and kind of shade them or highlight them as you go just to make sure there's no overlap. And these add up to 0.96. 0.7 plus 0.26 is 0.96. Now that would be a relatively challenging question to answer if we didn't have this tree. We'd really have to think super hard. But because we took the couple of minutes to lay this all out, these 5 questions were pretty immediate to answer. And that's what I meant that this is the only real property that we have to use other than some common sense and logic is that joint probability rule where we multiply as we go up the chain or we go along the chain. So this is what I encourage you to use when you're laying out probabilities.